The first reaction we're going to talk about for additions of alkenes is going to be the halogenation reaction. So we're going to start out with a simple alkene structure. And in the halogenation reaction, we're going to use a halogen such as Br2. We could also use Cl2. Okay? And so the product of this reaction is we're going to get an addition of halogen to each of the carbons involved in the double bond. So we'll form one halogen on a wedged bond, the other one will be on the dashed bond, and we'll also form the enantiomer of this. Okay, so let's go over the mechanism of this reaction. So redraw our alkene, and we'll give it a bromine molecule to react with. I'll draw in all the lone pairs. So in the first step of this reaction, we're going to have our alkene. It's going to act as a nucleophile. So the electrons that are in the pi bond are going to react with the bromine molecule, and we're going to have bromine, Br2, act as our electrophile. So the first arrow we're going to draw is from the pi bond to one of the bromine atoms. So we're going to have a nucleophilic attack arrow, followed by loss of a leaving group. Right, so we're going to break the bromine-bromine bond. At the same time, and this is what's unique about the halogenation mechanism, is that the bromine atom, we're going to take another lone pair, and we're going to have it react with the other carbon that was involved in the double bond. And this is going to give us a very unique-looking intermediate. So we're going to get an intermediate where we have a three-membered ring, and one of the components of that three-membered ring is a bromine atom, and that bromine atom is going to be positively charged. Right? So this intermediate here, where we have a positively charged halogen atom in a three-membered ring, is going to be called a bromonium ion. Okay? So you'll notice that I drew both of the bonds here on wedges. And this is because this is a concerted reaction. The addition of the alkene to the bromine molecule happens all at once. And this occurs from one face of our alkene. Remember, alkenes are planar. So it can either attack from the top side of the alkene or the bottom side of the alkene. So here we've drawn that the alkene reacted from its top face, and we have two bromines on the wedges. It's just as likely to have attacked from the bottom side, and we'll have bromines on dashes. Okay? And of course, we have our leaving group here, which is Br-. Okay? In the next step of this mechanism, we're now going to add in our second equivalent of halogen. So the bromide that we generated in the first step is going to act as nucleophile. And we're going to open up the three-membered ring. Remember, three-membered rings have ring strain because of the bond angles involved in this three-membered ring. So it's going to be highly reactive, so we're going to react with this carbon here, and we are going to open up the ring and give bromine another pair of electrons. So going forward, we have bromine will still be on a wedge on this carbon over here, but this carbon over here, our reaction is essentially an SN2 reaction. So we'll say this is an SN2-like step in our mechanism. So by doing that, the stereochemistry of this position is going to flip, where we're now going to have a bromine on a dashed bond. Right? And you get this product. The bromide is just as likely to attack the other side of the alkene, and if we did that, we actually get the enantiomer of this product. Okay? So there's a variation on this reaction. So I'll go ahead and draw our alkene again. We're also going to react it with bromine. This time we're going to do it in the presence of water. Okay, so a very similar first step occurs where we have our alkene act as a nucleophile, bromide or Br2 molecule is going to act as our electrophile. We're going to have loss of the leaving group. And we're going to have our bromine wrap back around on our alkene to form our bromonium ion intermediate. Okay? So when we do this in the presence of water, right, we're going to have a lot of water around relative to the number of bromoniums and bromide ions present. So in the case here, we have water is going to act as our nucleophile this time. So now water, with one of its lone pairs, can do the ring opening reaction, where a lone pair forms a bond to carbon. We're going to open that three-membered ring. Where we form our bromide product. And now we have a new bond. Remember, it's SN2-like, so we have inversion of stereochemistry at that carbon. And we have a new carbon-oxygen bond, right? And from this step, all we need to do is get a neutral structure. So we can have another water molecule act as base. So here we can do a proton transfer step where we deprotonate our protonated alcohol, and that will give us back our final product, which is a molecule called a halohydrin, where we have a bromine and an OH group on adjacent carbons. So this molecule is called a halohydrin. Right? And of course, we could have water attack from the other side of our molecule. So we also get the enantiomer of this molecule as well. And so this is the reaction of an alkene with a halogen. You're either going to form a dibromide, or if you do this in the presence of water, you're going to result in a halohydrin.